In the last segment, we focused on introducing Sn1 reactions, and we went through a list of the different observations that we could make about Sn1 reactions, such as the fact that the rate-determining step of the reaction involves only the electrophile, that is the molecule of the leaving group. We talked about how the reaction occurs best at tertiary carbons, second best at secondary carbons, and very rarely at primary carbons. And we also, with regard to the Sn1 reaction mechanism, we talked about how the reaction is not stereoselective. What we're going to do in this segment is we're going to extend onward and talk about why we can observe the so-called carbon skeleton rearrangements in an Sn1 reaction mechanism. And remember that the Sn1 reaction mechanism, as we start to set our minds up for thinking about that, is the reaction mechanism where the very first step of the mechanism is the slowest step. That's the step with the highest energy barrier. And that step involves breaking of the carbon leaving group bond to give a carbocation intermediate, much like we have the carbon-chlorine bond breaking here on the slide to give us a carbocation intermediate there as a result of that step. So let's get rolling. We're actually going to take a closer look at this starting material and the reactions that it can undergo using an Sn1 reaction mechanism to illustrate here in this segment the concept of carbocation rearrangements. Carbocation rearrangements are super fundamental to the field of organic chemistry. We're going to see carbocation rearrangements not only occurring for nucleophilic substitutions, but also for a bunch of other reaction types as well. And so we need to have a firm grasp on why carbocation rearrangements occur and how those rearrangements occur. So let's take a look at, to illustrate this concept of carbocation rearrangements, we're going to do a mechanism for a reaction that will involve a carbocation rearrangement. And this mechanism is otherwise going to look very similar to the Sn1 reaction mechanism that we did before. We're just going to be adding one extra step to do the carbocation rearrangement. So we're looking at the mechanism of Sn1 reaction now with a carbocation rearrangement. So I'm just going to put C plus rearrange. So we're going to do a C plus rearrangements. All right, so let's go ahead and get started with that. We're going to start with 2-chloro-3,4-dimethylpentane as our starting material. I'm going to fill in some specific chirality here so we can look at how the starting material relates to the product in terms of the chiral centers that we have here. So we have 2 chiral centers in this molecule that we're going to use as our starting material. We're going to react that with water, H2O. And typically when we see these reactions, you will either see them showing up as the electrophile plus the nucleophile, in this case water, or you'll see the nucleophile written over the arrow. That either way is totally fine. It's just 2 separate ways of showing the same thing. So we're going to try to predict what product would result from this reaction in this box here, using our mechanism as our tool to get to that final product. All right, so thinking about this reaction, what we know about Sn1 reactions already, about how the rate-limiting step of the reaction was that first step of the leaving group breaking away. That's always going to be the first thing that we need to do in an Sn1 reaction, is that the leaving group is going to leave. So step 1, leaving group breaks off. The leaving group is going to leave the building here. So go ahead and write that step out of our leaving group breaking away. And remember that we're going to break the bond between carbon and the electronegative atom because that's a relatively weak bond, and it's going to give a relatively stable product compared to breaking a carbon-carbon bond or a carbon-hydrogen bond. So we break that bond between carbon and our chlorine leaving group. The electrons from that bond go onto the chlorine because chlorine's the more electronegative atom. It's better able to handle that electron density than the carbon atom would be. We go ahead and write out our product that results from that step, and I'm going to go ahead and put in my positive formal charge here, and to dot all my I's and cross all my T's, I'm also going to go ahead and fill in my chloride anion here that has resulted from this step. So we got all that in place. Now what's going to happen next up is that at this point we have 2 options. One is that if we look back at the mechanism that we looked at in the last segment on Sn1 reactions, At this point, we would identify what the nucleophile is, and the nucleophile would attack our carbocation. In this example, though, rather than creating a tertiary carbocation that's the most stable type of carbocation, instead we've created a secondary carbocation. And the secondary carbocation is not as stable as the tertiary carbocation. And so what happens here is that if there is a way to move a methyl group or a hydrogen atom to create a tertiary carbocation, that's going to be what happens next. So after step 1, in any situation, if the carbocation is not a tertiary carbocation, what we need to be looking for is a carbocation rearrangement. And sometimes these will be possible, sometimes they won't. But we need to investigate further here to see if a carbocation rearrangement is possible. So when will a carbocation rearrangement be possible? As this second step, the carbocation rearrangement will be possible if we can move a hydrogen or a carbon over by one spot to create a tertiary carbocation out of a secondary carbocation. So let's do an illustration here to show what I mean when I say that we need to rearrange. So I'm going to show all of my hydrogens and carbon atoms at this region of the molecule explicitly here. So you'd have one hydrogen here. This over at the end is a CH3 group. That's a CH3 group. We've got a carbon right here. And that's going to kind of fill in the region that we're looking at for the molecule. So I'm going to leave the rest is line angle formula. Right now, that's a plus charged carbon atom. That is a secondary carbocation. So if we can do a so-called 1-2 shift to move a hydrogen or a methyl group to yield a more stable carbocation, we are going to do that. So we call this a 1-2 shift of a methyl group as well as the electrons that are bonded to that. So I'm showing the covalent bond there, or a hydrogen, which we call a hydride shift because it's a hydrogen plus its electrons. And we're going to try to do that to yield a tertiary carbocation, because if we can yield a tertiary carbocation, that means that this step will be energetically favorable because it would be going from a less stable secondary carbocation to a more stabilized tertiary carbocation. So by 1-2 shift, what we mean is that the only bonds that we can move are the bonds that will allow us to go from the carbocation, which we call position 1, and we can move only those bonds that are located at position 2, at the adjacent carbon atoms. So here we have 2 adjacent carbon atoms. So the options that we have for bonds that we could relocate, I'm going to highlight in green here. We could relocate that hydrogen and the electrons that are associated with that in the covalent bond. We could move this methyl group, CH3, or we could move any of these 3 hydrogens over here from the methyl group. Those would all represent, if we move those from position 2, which I've labeled position 2 as position 2 relative to the carbocation being position 1. If we can move those from position 2 over to position 1 to make a more stable carbocation, then we're going to do exactly that. So let's play around with this to try to determine what possibilities we could envision here. So let's say, hypothetically, that we take the electrons from the carbon bond here to do a 1-2 shift of the methyl group. So we move the methyl group over to where the carbocation is. So we take the methyl group and the 2 electrons that it's bonded to, move those over to the carbocation location. Let's show what would result from that electron pushing arrow set that we just showed here. So we still have a hydrogen right here at carbon number 3 of the chain. We have now moved the methyl group over to here, and there would still be that hydrogen there that was there from the start, so right there. And now if we look at where the positive formal charge is going to be in this molecule, the positive formal charge is going to be right here. Now you have to ask yourself, have we taken a secondary carbocation and converted it into something more stable, a tertiary carbocation? The answer here is no, we haven't. We've gone from one secondary carbocation on the left to another secondary carbocation on the right. That positively charged carbon still just has 2 bonds to other carbons, so this product is not any more stable than the reactant. And so therefore, there is no motivation for the reaction to take place as written. We need to find some other route to do a carbocation rearrangement. So I'm going to erase this structure that we just drew out here because we've deemed that to be not possible, not correct. And I'm also going to erase my electron pushing arrow here because we've deemed that that is not what's going to be going on because it doesn't improve the stability of the molecule. There has to be an energetic motivation for this step to take place. The energetic motivation is that we would be going from a high energy starting material to a lower energy product out of this step. So rather than moving a methyl group in this 1,2 shift, let's instead do a hydride, a hydrogen, to see if we can do that to yield a tertiary carbocation. So again, we're looking at this being called a 1,2 shift, which means that going from position 1, where the carbocation is, to position 2, we have to be moving one of those bonds at position 2. So we're moving one of the bonds that we've shown in green. We already tried the methyl group, it didn't work. So now we're going to try this hydrogen to do a so-called hydride shift. So hydrogen comes over from position 2 to position 1, hence we call it a 1,2 shift. And we're going to write out what would result from that to see if we can do this in order to get that stabilized tertiary carbocation. So I'm going to draw in the groups that were green, still green right here with our methyl group. And our hydrogen has now moved over to here. We did that 1,2 shift. And now if we take a look at where we are below the octet, in other words, where is the carbocation going to be? The carbocation will end up right here because that carbon, carbon number 3 of the chain, originally had 4 bonds to it over here on the left. Now that we moved that hydrogen over to the next carbon atom, that means that our carbocation is going to move. So in other words, we did a carbocation rearrangement. We moved the location of the carbocation by 1 spot. In other words, we did a 1,2 shift. So now we ask ourselves that key question about whether we're on track or not. In other words, have we taken a secondary carbocation and converted it into the more stable tertiary? We started with secondary. On the left is the one on the right, a tertiary, and the answer is yes, absolutely it is. So this is absolutely our tertiary carbocation on the right because it has 3 bonds connecting that positively charged carbon to other carbon atoms. So therefore, this is going to be the second step that we would do of this mechanism. And this step, step 2, is a step that you won't see in every single Sn1 reaction, but you will see it any time that you can take a secondary carbocation and do a rearrangement, a 1,2 shift in other words, to make a more stable tertiary carbocation. And it will always be that the rearrangement has to involve just moving from the adjacent carbon atom over to the carbon that is the carbocation. You can't have atoms jumping all the way across the molecule. It always has to be just this 1,2 shift going from position 2, where we have groups bonded there and highlighted in yellow that can move over, to position 1, where position 1 is defined as where the carbocation was. So that's what we call our 1,2 shift here. So onward to step 3 of the mechanism, and from here, hopefully this is going to look very, very similar to what you were doing in the earlier Sn1 mechanism example in the last segment, where we didn't have the carbocation rearrangement. So the only thing we've changed here is that we've done that step 2 because of the fact that this step is super duper energetically favorable because it's making a more stable intermediate. So it's going to be very energetically favored because of the fact that we're going from a secondary carbocation that's unstable to a tertiary carbocation that's more stable. Okay, so that tertiary carbocation, even though it's more stable than secondary, is still very charged and eager to react as an electrophilic carbon. So that's exactly what's going to happen at step 3 here, is that the carbocation electrophile gets attacked by a nucleophile. So the nucleophile attacks the carbocation. All right, so we're going to just take that carbocation intermediate that we finished up step number 2 with. That was our tertiary carbocation intermediate right here. And we're going to look for what our nucleophile is in the reaction mixture. We had water. Water has a lone pair of electrons, so that's going to allow it to act as a nucleophile. Remember, a nucleophile has to be something that has a lone pair or a pi bond. Otherwise, it is going to be a no-go as a nucleophile. So we're going to use that lone pair of electrons as our source of forming a covalent bond to the electrophilic carbon. So we come over and form a covalent bond to the electrophilic carbon using that lone pair of electrons from the oxygen. So let's go ahead and draw out the product of this step of the reaction mechanism. And I am going to go ahead and show the stereochemistry here at this step, because remember that at step 3 here, we started off with our carbocation being trigonal planar, because the carbocation just has 3 regions of electron density. And so the water nucleophile can attack it from either the top face of the molecule or the bottom face, leading us to a mixture of the R and the S chiralities at that location. So let's go ahead and we'll fill that in here into the skeleton that I'm working on there on the product side of the equation. So we'll have the 2 different chiralities. So we're going to show the methyl group as a wedge, and the water that's bonded now to there as a dash to fill in our tetrahedron. Put a positive formal charge on it. And the other product that would be formed here would be the enantiomer of that. So there's a few different ways that you can accurately draw the enantiomer. One of those is that you can just switch all the groups that are on wedges to dashes and dashes to wedges. So that's what I'm going to do here as one correct way of doing this. The other is you could have envisioned drawing the mirror image of the structure on the left. So this is going to be our enantiomer of the structures, our racemic mixture, in other words, an equal mixture of the R and the S chiralities that was born due to the fact that the water nucleophile can attack from either the top face of the molecule or the bottom face of the molecule. All right, we are almost to the end here, almost to that final product that we're trying to get toward. And looking at this, in order to get to a final organic product that has no formal charges, what we need to do last here is a deprotonation step. So this is our quick acid-base reaction where we're going to lose a proton from our organic molecule in order to give us a stable neutral molecule with no formal charges in it. So we're going to take both of those 2 enantiomers from the earlier step. I'm going to show just one of them here to illustrate what's happening in the reaction mechanism. It would be the same process occurring at both of those 2 stereoisomers there that resulted from step 3. So we're going to deprotonate those, and we look around, we ask, what do we have available that would be statistically probable to come into contact with and be able to act as a base? What we have is anything that has a lone pair of electrons technically can come in, and water is going to be our best base that we have there. So we have lots of water in the reaction mixture, so the lone pair from the water comes over, acting as our base to grab a proton from our so-called acid. Acid by definition because it's losing a proton during the course of the reaction. In other words, it's being deprotonated. And that's going to give us our final product of this reaction. So we're going to fill in OH here, our alcohol functional group in the final product. And we would also be generating, as a result of this, H3O plus by taking H2O and grabbing that proton. We can go ahead and draw both of the enantiomers. Which I will go ahead and do right here. So to do both of the enantiomers, I'm going to just flip my wedges and dashes here to go ahead and give us the 2 enantiomers that would result from this overall process. So our final product here in accomplishing our goal of getting to the final product of this reaction will be both of these stereoisomer products. So with that, hopefully you have a better understanding of the concept of carbocation rearrangements. That's the new thing that we've introduced in this segment. And you should be able to apply carbocation rearrangements to the type of the reaction that we've shown here. You should understand why those occur. They occur because they are energetically favorable to take a less stable, less substituted carbocation and make it into a more stable, more substituted carbocation. And you should be able to incorporate that now into your Sn1 reaction mechanisms for predicting products.